So good afternoon. We already started our chapter that is called shallow foundations. So in last class we have some introduction about the foundations and what is foundation. Then we discuss about the why do we need to think of a foundation for a structures. Then different types of foundations we have discussed. Okay, here, and then particularly we saw a map like. Okay. So since we are discussing about the shallow foundation in this chapter, so we did in details explanation of the shallow foundation types. Then we discuss when do we select the shallow foundation instead of deep foundations, and then the bearing capacity. Okay, and after that we have discussed about the three types of soil failures or capacity failure of soil due to the foundation load. Okay, so today we'll be discussing from this one bearing capacity equations development. Have a look in the beginning of the equation development for the bearing capacity. Tarjagis he developed first the equation for bearing capacity of soil. So in last classes we have seen that bearing capacity calculations is important for us, right? And since it is very important, so we need to develop some sort of equations. So many of the researchers tried to develop, but he was the first person who gave a comprehensive equations on this bearing capacity of foundations. Okay, so what he did, Tajagis in 94 he developed the equations, was the first person to develop the theory of a on ultimate bearing capacity of rough shallow foundations. So normally for the shallow foundations he developed the equations. Then a foundation is shallow, its depth. So in last class I have said that okay, not only the type we will consider the shallow, there might be some uh, numerical considerations that we will call it shallow foundations. It's like that. If you find your width of the uh, foundation is higher or equal than your depth, so that time you call it what? Shallow foundations. Or in other way, if depth is less than or equal to the width of your foundations. So suppose this is the foundations you have, suppose this is the width. Can you see the picture? Okay, so here I was discussing that if the depth is less than or equal to your width of the foundation, that we call B. So here you can see this is the foundation and this is the width of the foundations B. So if it is less than or equal to this, the depth, you are considering DF. Can you see the DF? So that time we call it shallow foundations. And later investigators suggested that foundations are shallow if DF is less than or equals to the 3 to 4 times of B, right? So these two conditions are here to find out the shallow foundations, or based on the depth if you want to say it is shallow or deep. So like this you can consider. A continuous or strip foundation is one whose width to length ratio is almost 0 or approaches to 0, B by L equivalents to 0 or tends to 0 you can say. So what does it mean? Do you remember the strip foundation explanation that I gave last class? I said if it is very long, right, but width is very small, right? So that
Yes,
time we
sir.
call it strip foundations. So simply if you consider that width to length ratio, last class I gave the example, if it is
Yes,
0.3
sir.
meter and this is 30 meter or maybe 10 meter or 20 meter, suppose whatever it is. Suppose it is 20 meter and this is 0.3 meter. This is 0.3 meter. So if you divide 0.3 by 20, so it's very small, right? Which is tends to
Yes, sir.
0. So this kind of footing we call strip foundations, right, or strip footing. Is that clear?
Yes, sir.
Okay. So the effect of soil above the bottom of the foundations may also be assumed to be replaced by equivalent surcharge. Suppose you can see this is the bottom of the foundation, right? This is the bottom
Yes,
of the
sir.
foundations. So above this you have some soil here. If you just consider this one, you have this soil, right? This side and the right side also. So this soil also have some force. Also it will give some force to the foundations because it has
Yes,
self
sir.
weight and other pressures also. So this kind of load we are calling surcharge. So even though if you have some soil inside in here, right? Maybe in this portion you have, sometimes you'll find. So that is also will count as a surcharge. You understand?
Sir, if there is no soil, then
Sorry, sir. Can you repeat it, sir?
If there is no soil, no problem, no surcharge there.
Oh, yes. Yes,
okay.
sir.
If there is no soil, no surcharge, right?
Yes, sir.
Okay. So here you can see uh, this is the situation when you have the footing scenario. Okay, so this is the column, suppose pedestrian column you are having here, and this is the basement of your footing, and the column is transferring the load to this footing, and footing is transferring to the load to the soil, and this soil we are considering the foundation soil. Do you understand the thing? Okay, now you can see the failure zone under foundations can be separated into three parts. So this is actually the failure activities as I discussed in last class, right? This is the failure one line. This is one failure line. Another line is this one, right? It stops here. Another line is here, right? It continues up to here, and even it continues like this, right? This is the ultimate soil layer. That is the top layer of soil, and this is the bottom line of the what foundation. So that's why this failure zone under the foundations can be divided into three parts. What are these? They first consider this triangular part, A, C, D. Can you see this one?
Yes, sir. Yes, sir.
That A, C, D they first consider.
D.
Okay. The radial shear zone ADF and CDE. Can you see this?
Yes, sir.
ADF. Right, this one.
Yes, sir.
And CDE.
E.
So this is radial we can see, and then rest of this curve is another curve is like this up to E to G. Okay, and you can see DE and the DF. So DE and DF.
GF.
Okay.
Sir, up to E to G, sir.
Yes, this one E to G is the curve. So the radial zone is ADF.
ADF and CDE, sir.
Okay, and CDE. So here you can see the curve is up to here, right? But the curve continues to G point, up to G point. And this curve continues up to this H point.
H point.
Okay. So I'll come to this also. The two rectangular Rankine passive zone, that is AFH. So this one actually, that continuation as I said. Okay, this one is Rankine passive force. So there are two kinds of force in a from the soil actually. So if you consider this is a retaining wall or something, okay, suppose if we consider this is the retaining wall, so if you have soil here, so this kind of force is your active pressure. Okay, and if you have the soil here, this force acting in the foundation will be your passive force. Okay, you understand the Rankine passive force pressure?
Yes, sir.
Suppose this is the retaining wall, this one, and you have the soil in this side. So whatever the force is acting here, right, to tilt it down, this kind of force we consider the active force. But what are the force is acting to slide your structure, slide the foundation? Are you getting the concept? To slide the foundation, that is sometimes we call Rankine passive force. So this force is this one. Okay, this zone we consider this force which relate to the sliding failure of the foundations. Is that clear to all now?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, so if I again repeat these portions, so the triangular zone we consider ACD. Here you can see ACD. This is the triangular zone for the failure surface that is immediately after the foundations, like just below the foundations. And the radial shear zone ADF, you can see ADF. This is the radial zone, and CDE and CDE. So here curve is DF and here curve is DE, but this is extended up to the point G, and this failure line also extended up to the point H.
H.
So this extended portion or this portion we consider the Rankine passive force. Okay.
Yes, sir.
So usually you will find the foundations is failing on this way. So that is the consideration from the Tarjagi's equations. That is the main considerations from his equations. Or based on this situation, he tried to develop the equations. The angles CAD and ACD. So that means the angle A and angle C both are assumed to equal to the soil friction angle. Okay, so these two are equal. And surcharge Q. So we already have seen in the last slide that surcharge Q, if we consider, right, on this one, the failure surface GI and GH. Have a look. Surcharge means from here to this, right? This is the situation of your surcharge condition just above the bottom. So here you can see this is the line G and I and H and J. So these two are neglected, right? So in his equation he did not consider these two failure surface. Okay.
Yes, sir.
So considering these failure surface or failure lines, he tried to develop an equations based on the equilibriumity. So he developed these equations for continuous or strip foundations. So I think now it is clear which one is continuous and strip foundations. This is the formula for the continuous or strip foundations. So that is Q ultimate equals to C prime and C and Q plus half of the gamma B and gamma. So what are these? If you just try to understand the formula, just for simply, that is, have a look. That is the C prime, the cohesion of soil, right? So this is the stress from the soil, right? So from the cohesion property, what is the stress on the soil you are considering? Then what you are considering? Q, right? So this is the what is called stress on the soil, which locations you are having the load. So that is, we consider Q into, sorry, unit weight of soil into dF. Suppose if you are here, right, at this location, you want to know the stress or capacity, sorry, stress of the vertical stress of the soil. So what you will do, if you know the unit weight of the soil, right, so you can simply multiply with the dF, as I said in the last class. If
Yes, sir.
gamma is given, gamma is given, so gamma is what? Some weight versus meter cube, right? Some load versus meter cube. Suppose if it is
Kilonewton per meter cube.
kilonewton per meter cube,
Meter cube.
right? So you can cancel it out. So it would be square. So if unit weight is kilonewton over meter cube, right? So if you multiply with the depth, so if you multiply with the depth means what? Meter,
Yes, sir.
right? So then it will become meter square. So kilonewton per meter square. So it equals to your stress. Okay. And then NC, NQ and gamma. Okay. Oh, one term is left. So half into that is gamma into B into N gamma. Okay. So that is actually the area of the soil covering. And these NC, NQ and N gamma are the bearing capacity factors that are non-dimensional and are functional only the soil friction angle. So these three parameters or three bearing capacity factors are depends on the frictional angle only, right? So researchers develop these factors based on the friction angle. So for different soil locations, you might have different friction angle. So based on that, you have these changes, right? So if the soil, you have the cohesiveness, if the soil is cohesiveness, so that time you will find some cohesive stress, right? And normally you get always the Q, the stress at the locations on the soil, self weight effect on the soil capacity, right? So these three things they combine, so that's why it's calling equilibrium equations. And by combining these three capacity, he developed one capacity, that is we are calling bearing capacity. So this formula is developed for continuous or strip foundations, so both are same. Now what happen if your foundation is like square foundations, is like circular foundations, right? So that time you change some value. So we have seen this for continuous or strip foundations, this is the formula. But for whenever you are coming to the square foundations, so that time you change this with another factor. So you are multiplying extra 30% in the cohesive term, right? And
Yes, sir.
but you're reducing little bit. Half means what? 0.5, right? This half
Yes,
means
sir.
0.5.
10% reducing, sir.
So here you reduce 10% while it is circular. Okay,
Yes,
so weight
yes, sir.
effect. And this is for the sorry, this is for the square, and this is for the
Square.
circular. So
Circular, sir.
circular, the in case of the cohesiveness, the factor is same like the square, but in case of weight effect, right, in
Yes,
weight
sir.
effect, it is also reducing another 10%, you see.
Yes, sir.
So if you just
Yes, sir.
simply understand this formula, you can, one formula if you understand, then other formula is easy for you. Because for the
Yes, sir.
square, they reduce 10% and increase 30% for this cohesiveness, and reduce 10% for the weight issues, right?
Yes,
And
sir.
similarly another 10% for this. So these are the informations are for general, what kind of failure? General type failure. So these are the formulas can be used for the general shear failure. So in shear failure, we have seen three kinds of shear failures. So, and if you have the idea about the general shear failure, so we can see for the local shear failure, they also develop the equations. So you just need to just adjust some factors. So have a look for this local shear failure for the strip foundation, that means the continuous one, they they reduce some, right? This is 2 by 3, so around 67 point something, right? 66.6, this percentage. So this is reduce 33%, right, for the strip one. And when it is these ones, so they're multiplying some other factors. So similarly for square footing and circular footing, you can see. All right.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay. So now you can see the factor of safety. So can anybody tell me what is factor of safety?
Yes, sir. If there is load is maximum, that time we can decrease the load for our safety purpose. That's why we and take it allowable load. That's why we divide some factors that called factor of safety.
Okay, it's a good answer actually. Okay, so many a times in structures you will find that you cannot give the assurance that whatever you are calculating, that is 100% right. There are so many uncertainties, right?
Yes.
Are you getting?
Yes, sir.
Yes,
Okay.
sir.
So there are so many uncertainties. That's why whatever the ultimate loading capacity of soil we have, we try to do some factorizations. Then we can use the safest maximum value for the structures, or safest maximum value for our design. Okay.
Yes, sir.
Okay, then you will
Sir,
find
is it for unwanted load
this is
or
this is
uncalculated?
uncalculated, not unwanted. But while you do the calculations or while you go for the structures, you know there are so many uncertainties might be there. Okay, and you are not confident enough of sometimes you are not confident enough with your test equipments, testing parameters. So many issues are there, so that's why you want to keep your structure in safe mode.
Yes, sir.
So it depends, it varies country to country. If you are in Bangladesh, maybe you are using 3. If you are in maybe USA, you are using maybe 2 or less than 3 or maybe 2.5. It depends on the standard of that country, right?
Yes, sir.
So that's why I asked you the question or example, like if you have the capacity of taking 50 kg of load, if I give you 40 kg, so you will feel more confident, right? On walking,
Yes, sir.
maybe if I say, okay,
Yes, sir.
you walk 1 kilometer with this. Suppose this is your target, but some of you will feel no, I will not take 50 kg, I will not take 40 kg, I will take only 20 kg. I want to I want to stay in more safe side, right? Some
Yes,
of
sir.
you may
Yes, sir.
some of you maybe say, okay, no, I will take 50 kg. This is up to you. It depends on what? Depends on what?
Depends on capability, sir.
Depends on the
Not
depends
capability.
on depends on the user applying load.
Depends on the
Sir, design, sir.
not design. Depends on the
Uh,
confidence.
Depends on the people, sir.
Depends on the confidence. You understand?
Sir, depends on safety.
No. Depends on the confidence. I'm talking about the example that I made. So in people, those
Okay, sir.
people are really confident. They said, okay, I can take 40, 45 like this. But those people are not self-confident. They'll say, okay, I might fall. I might be getting tired. So, okay, I'll take 20, 25, 30. You understand? So
Yes, sir.
Yes, sir.
similarly in design also, you'll find some designers are confident enough with their calculations. So that time they go a little bit more precise dimension, precise shape. Or if they are if they are confident enough about the testing quality of the materials. Suppose the company of soil testing company is very good, and I have very personal confidence about the company, so that time I can consider, okay, this might be like this. So who set the code in the Bangladesh or in other country, they consider all the issue in mind, and then they said, okay, for Bangladesh we will be using 3. You understand that point?
Yes, sir.
Okay, so now come to the allowable bearing capacity. What is allowable bearing capacity? Is the maximum bearing stress that can be applied to the foundation such that it is safe against the instability due to shear failure and the maximum tolerable settlement not exceed. So on which capacity it will not go for instability and it will not go for excess settlement, that one or that capacity you call allowable bearing capacity. Okay. Okay. The gross allowable bearing capacity of shallow foundations requires the application of factors that is we call safety of factor. So normally we consider that is QAL divided by QU divided by factor of safety. Okay. So that time we can consider this is actually the gross. Okay. Why we are not considering the effect of surcharge here? Are you getting the point? Okay. So in case of net allowable load bearing capacity, so here we are considering the effect of surcharge. So the net stress increase on soil, net ultimate bearing capacity. So it would be allowable capacity for net, that is net ultimate capacity divided by the factor of safety. So what is net one? That is QU minus by Q. So that is your surcharge soil, right? You reduce the capacity of surcharge from the actual soil below the ground. Okay, so that time if you replace this Q net, QU net here, right? So it would be QU minus Q. So that is the factor of safety calculation for the net one. Okay, so whenever you are considering the capacity, when you are considering the surcharge soil, so you are having the less capacity of the soil, little bit less, right? Because you added the load of the surcharge, but technically you are reducing the stress of the surcharge from the capacity. Do you get this information clearly?
Yes.
In technical,
Yes, sir.
in technical sense, you are saying, or you are maybe visualizing that okay, surcharge is the above the bottom line of the foundation, so we have to add the stress. Why it is reducing, right? So you are adding the load, so this load is reducing the capacity of the what? Capacity of the soil. Do you understand this part or not? You do not ask the questions, how can I understand?
Yes, sir.
Yes, sir.
Suppose this is the footing, right? So under this footing or below this footing, you calculate the QU. Suppose this is the capacity of the soil, you already calculated. So now you calculate the soil without considering the effect of surcharge, right? So these depths, right, or this soil effect. Okay, so if you
Yes,
do not
sir.
consider, so that is your gross one. But if you consider this effect, so what happened? You are applying some load here, right? So this load
Yes, sir.
ultimately
Yes, sir.
producing some stress. This load ultimately producing some stress. So this stress will be
Yes,
reduced
sir.
from this stress. So then in such a way that you are mathematically removing this soil, and you are finally calling that this is ultimate soil. Sorry, net, right?
Net. Yes, sir.
Okay. So up to this is clear, then we can do one example, though it is done in the book, but just to give you some idea. A square foundation is 2 in plane, like 2 meter by 2 meter. So you can consider this square foundation. So what does it mean? You first go to the general formula development and you go to the square. So one information you find, that is foundation type is square. The
Yes,
soil
square.
supporting foundation has a frictional angle is 25 degree. So you
25 degree.
got the frictional angle, and C prime, that is the, what is C prime? Cohesion stress, right? So that means this is
Yes. Yes.
this is the cohesive soil. Okay, and the unit weight of soil gamma is given 16.5 kilonewton per meter.
5
Okay.
kilometers.
Determine the allowable gross load on the foundation with a factor of safety how much? 3. And assume that the depth of the foundation is 1.5 meter and that general shear failures occurs in the soil. So all the informations, what kind of failures? General shear failure. So which formula you need to follow? General shear formula.
General shear failure.
So this is, there is no picture because all the informations are
Yes,
given
sir.
here. But if I just try to give you the examples illustration by drawing a picture, so you can see this is the conditions, right? Maybe this is the soil, top soil you have. Okay, so this depth is how much? How much? 1.5.
Sir, 1.5 meter.
So this is 1.5.
5 minutes.
Okay.
5 meter.
Okay, this is 1.5 meter. Suppose this is your footing or foundation, that is we consider square footing. So what is the dimension of this? 2 by 2 meter square.
2 by 2. Yes,
Okay.
sir.
So we got the phi value, which is 25, this and this. So just we need to find out the capacity, right? QU for this soil.
Yes, sir.
Yes, sir.
Yes, sir.
We need to calculate the QU of the soil. So all the informations are given, right?
Yes, sir.
Yes, sir.
So what is the formula?
Yes, sir.
This formula, right? So have a look in this formula.
Second one.
Oh, sorry.
Second one.
Yeah, that's right. Okay, so you are in class now. So square foundations. So square foundations is given in the question. So you can see C prime is given. Q, right? Q can be found, and gamma is given, right? So how can you find the Q?
Sir, Q equal to gamma into DC. DF.
Very
sir.
good. So if you just simply multiply Q into
DF,
gamma
yes,
into
sir.
DF, so you can get it. Okay, and B is also given. B is 2.
Yes, sir.
So you need these bearing factors. So now to
NQ and N gamma.
get this bearing factor, there are some equations and there are also some table. So from book you just look into the equations. So I'm now showing you the table to calculate this. So have a look for phi prime, right? So for phi prime is 25
Yes,
degree.
sir.
So for phi prime 25 degree, and C you can find 25.13, and Q you can see 12.72,
12.7.
right? And N gamma is
Yes, sir.
8.34.
3, 4.
So if you know these all
8.34.
values, right? So now you know all the informations of this formula. So can you do this problem?
Yes,
Yes, sir.
Yes, sir.
So you just simply write the formula and you just put all the values. It's as easy as it is, right? So just for your illustration, you can see this is the formula we are using for the square footing, and these are the values we have seen from here: 25.13, 12.72, 8.34. Okay, so you put all the informations here and you replace the formula with these equations. Okay, so you find that your QU is this much. Okay,
Yes, sir.
Yes, sir.
so they want to know allowable load, right? Determine the allowable gross
Yes, sir.
load. So that's why you need to find out the maybe a small q, that is the allowable one, gross, right? Why it is happening like this? So and which is the allowable, A double L? Why it is automatically taking like this? Okay, so you have to find this. So you already get it, right?
Yes, sir.
So you already get it, this
QU. Yes,
QU,
sir.
right?
Yes, sir.
So
Yes,
now if you just simply consider your factor of safety here, so you can get out get the value of what? QAL, right?
Yes, sir. Yes, sir.
QA.
Okay.
Yes, sir.
So with the factor of safety you can find out the QAL, a level case. So if you simply just divide this QU, that is you calculate it, and divide by 3, so you found the value is 1078.29. If you divide by 3, it's like this, 359.5 kilonewton per meter square. And now you got the stress. You got the stress here for maybe you got the stress is how much? 300 something or something. Maybe stress we consider kilonewton per meter square. But they said you need to find out the load. You need to find out the load. How much load can be taken by this soil, right? So what will be the total load of this? So you know the area is 2
Sir, stress into area.
yes, you know the area is 2 into 2. So if you simply multiply the QAL with this, so you get the
Area.
not area, you get the load.
Area. Yes, sir.
So you get the QAL, that is we are considering load. You clear now?
Yes,
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so simply you can see, you just multiply the area and you get it. So in that case, what does it mean? That means foundation can take this much load if you are thinking of this foundation,
Load.
right?
Allowable load. Yes, sir.
Okay, so if your column is having this much load for this kind of foundations, that means your foundation can take if the column load is less than this. But in RCC you do in just little bit different way, right?
Yes, sir.
But the concept is similar.
Yes, sir.
In RCC, what you do, you calculate the load on column and you check the dimension of the foundation, right?
Dimension of the column.
Not dimension of the
Yes, sir.
column, dimension of the foundation. You in RCC, how do you design? Usually you have the column dimension, you design the foundation dimension. But here, okay, this is the analysis part and you do the design there. So you are analyzing that, okay, if this is the foundation, how much load this foundation can be taken, or how much load you can provide on this foundation, right?
Yes, sir.
Yes, sir.
Yes, sir.